Welcome to Beam College, everyone. I'm Shenping Huang, a software engineer at Google and an active contributor to Apache Beam project. Today, I will be introducing a new Apache Beam feature that allows users to perform real-time anomaly detection. Alright, picture this. 4 friends in the class just got their test results back. 3 of them totally aced it, 96, 100, and 94. Then bam, one of them sees an 80. It's like, wait, what? Where did that come from? Maybe they struggle with some of the concept in the test, or maybe they somehow skip an entire page. Whatever reason, the score of 80 is definitely the odd one here, and that is what we call an anomaly. Simply put, an anomaly is a data point that differs from the norm. An anomaly detection is to find these outliers. Anomaly detection is useful in various scenarios, including in our above example, helping teachers adapt their teaching methods based on score anomalies, or allowing sensor data analysts to spot malfunctioning equipment. The definition of anomaly depends on what we define as normal, based on the average or the majority. It also matters how we measure deviation, by distance, density, or other metrics. These considerations lead to different detection approaches, and anomaly vary based on data types, which we will explore on the next slide. Anomaly can exist in different types of data. We encounter them in bounded datasets, such as a company's quarterly sales figures, where data has a clear start and end. We also see anomalies in unbounded streaming datasets, like network traffic data, where data flows in indefinitely. Anomaly can be univariate, like the outliers exam scores in the previous example, or they can be multivariate. Consider a person shooting arrows at a target. If most arrows cluster around the bullseye, an arrow landing far off to the side would be a spatial anomaly, represented by its xy coordinates. When analyzing unbounded data with timestamps, anomaly can appear in different ways. Here we talk about 2 scenarios. First, in data streams, we often assume data points are independent and identically distributed, also called IID. An example is the temperature in a climate-controlled data center. Unusual temperature spikes could indicate HVAC issues or even something more serious like a fire incident. Second, in time series, data points have temporal dependencies, like the daily number of New York taxi rides, which has a seasonal pattern, and the spike here could be due to a rainy day. Finally, for data streams, some may exhibit concept drift, where the underlying data distribution changes over time. As shown in this picture, the distribution shifts midstream and then shift back again. This could happen if a sensor goes bad and then it is back to normal after recalibration. Detecting these change points and adapting our models accordingly is crucial for accurate anomaly detection in such cases. It's also worth noting that our current implementation primarily focuses on anomaly detection methods for data streams, with time series methods planned for the future. Having explored the various types of anomalies in the previous slides, let's now discuss how Apache Beam can help process this data. This one-pager covers most of the fundamentals of Beam. Apache Beam is a framework designed to unify both batch and streaming data processing. Key concepts include P collection, which represents data for parallel processing, P transform, representing computations to transform data, and pipeline, which is a DAG of P transform. The data flows from a data source through various P transforms and finally to a data sink. In this visualization, I prefer to show P transform as graph nodes, which aligns with how pipelines are constructed with Beam SDKs. Each P collection connects the P transforms, serving as the output of one and the input of another. Beam provides a library of P transforms for operations like map, flatten, group by, reshuffle, etc., as well as more recent machine learning functionalities. If you are also interested in these topics, please check out other sections in Beam College. As one of the latest ML-related P transforms, anomaly detection is implemented in Beam Python SDK. To use it, simply choose a detector and apply that to your P collections within your pipeline. Let's first consider the P transform is a black box and look at its input and output structure. Each element of the input P collection is a key beam row. Here, a beam row is an immutable tuple-like structure defined in Beam, and we use it to store the data. The output element is a key value pair. The key remains the same as the input, while the value is a data class incidence containing the original data in green and a list of prediction results, possibly from different detection methods. Each prediction result includes model ID, the anomaly score in yellow, the threshold used to determine an outlier, and the predicted label in red. 0 is for normal and 1 is for abnormal. To understand how anomaly detection P transform works, let's examine its internal component. At the core, we have individual detectors. These detectors run specific anomaly detection methods to generate either anomaly scores or labels. In the current implementation, we support statistical methods like incremental z-score, IQR, as well as offline models such as isolation forest, one-class SVM from the PyOD third-party library. Each detector component can optionally include a threshold criteria subcomponent. Without a threshold criteria, the detector simply outputs outlier scores. However, if a threshold criteria is specified, it's used to assign labels to the scores. For instance, with a fixed threshold of 3, any data point with an outlier score exceeding 3 is labeled as an outlier. Currently, Beam supports two thresholding methods: fixed thresholding, which uses a fixed cutoff value, and quantile thresholding, which calculate and use a quantile, for example, the 95th percentile, as the threshold. Building upon the concept of individual detectors, we also provide ensemble detectors. They can run multiple sub-detectors in parallel and then aggregate the resulting scores or labels. Notice that these subdetectors can be individual detectors we saw earlier or other ensemble detectors, which means that you can have ensembles within ensembles and so on. The specific aggregation logic is determined by an aggregation strategic subcomponent. we have two types of aggregation. Score aggregation, such as calculating the average of all outlier scores for each data point, and label aggregation, for instance, an outlier being labeled only if a majority of sub-detectors agree. Typically, we see three usage patterns for ensemble models. Ensemble detectors. First scenario, if we have an ensemble of homogeneous subdetectors, meaning they all use the same anomaly detection method, then it's useful to combine their outlier score to get a single aggregated score. Second scenario, again, with homogeneous subdetectors, we can add a threshold criteria directly to the ensemble itself. This way, we apply the threshold to that combined score and get a final normal or abnormal label. Third, or heterogeneous subdetectors, where each uses a different methods and their scores might not be directly comparable. We will add a separate threshold criterion to each individual subdetector inside the ensemble. Then we will aggregate the resulting labels based on our chosen strategy. Now, let me switch to my notebook window and do a quick demo. So in this notebook, I'm going to demo how we can use a norm detection p-transform on both batch and streaming data. So I'm going to skip the preparation steps. And the first part of the demo showed how we use a norm detection on batch data. And we first generate synthetic data with outlier. And let's plot out what and show what the data looks like. So we can see the data follow the same distribution, but we also introduce some outliers here. Next, I'm going to run the Beam pipeline for this batch data. Notice that the pipeline is very simple, so we first use the create p-transform to get the data, and then we have a map transform to convert the data to the row format we mentioned before. And we also need to add a key to these rows. And then we applying our anomaly detection p-transform with the z-score detector. And then we filter the result and only show the outliers. Okay, let me run this pipeline. Here, the result shows there are two outliers here in the data. So I think that will be the outliers here and here. Okay. In the second part of the demo, I'm going to show how we're going to use the transform for the streaming data. Again, we first generate the synthetic data, but this time we try to introduce concept drift. Again, the concept drift means that we are going to change the underlying distribution of the data. Okay, let me first generate the data and then again plot the graph. So every 200 data points, the data remains the same distribution, but after this first 200 data points, we can see that the distribution is changed, and then it changed throughout the timeline. So I'm going to set up the pub/sub and publish this data inside the model. Okay, so let me set up the pub/sub, topics, and publisher and subscribers. We are going to publish the synthetic data set to the pub/sub, and then inside our pipeline, we are going to read from the pub/sub and do the anomaly detection, and then also generate the result and send it over to another pops up, output pops up. Okay, so I'm starting to publish the data to the pubsub, and also launch my Beam pipeline. Notice that the Beam pipeline here is very similar to the batch, the pipeline, but here we need to have the I/O here to read from the pubsub, and then we convert the pubsub message to the Beam rows and add keys here, and then we have a norm detection P transform again with a Z score detector. And notice a small note here is that we are using the sliding window means and sliding window standard deviation here. And at last, we are going to convert the output to the pubsub message and send it to the output pubsub. Okay, and I'm going to run another piece of code to collect the result from the output pubsub and plot it out. Okay, let's see how many data points we have already collected here. 121. Okay, let me start the plotting code. So here, every 5 seconds, we will take a snapshot of what's inside. So we can see that the data is already streaming in, and the output is generated. And we can see here that, the data, we find the outliers here, but when the distribution change, we know our algorithm can find the change points and consider them as outliers. But as more and more data from the new distribution streams in, we are not going to consider like this point as outlier again because the model adapt to the new distribution. So so this data points, even though it looks like outliers, they are not outliers again because under the new distribution they are not. And under the new distribution, so this is the outlier because it's deviate from the distribution, the norm a lot. Okay, I have another demo for showing how to use the in-sample models to do outlier to do anomaly detections, and I want to show how we can use the offline isolation forest model or LOF model, but due to the time constraints, I think I'm not able to demo that live. But feel free to check these demos, and the links will be available at the end of the presentation. Let me switch back to the presentation. All right. So in summary, I've explored the anomaly detection features in Apache Beam. So the key advantage of using the P-transform mirror the core strengths of Beam itself. First, Beam allows you to create a single pipeline for anomaly detection on both historical and real-time data. This unified approach simplifies development and speeds up the creation of robust solutions. Second, with Beam's distributed processing capabilities, you can efficiently detect outliers in your data without worrying about how your computation is handled in parallel. Third, Beam supports a wide range of anomaly detection algorithms and custom transformations. It can be tailored to meet different specific requirements. Last but not least, the anomaly detection pipeline you build can run on multiple execution runners like Apache Flink and Google Cloud Dataflow with minimal modification of code. For those who are interested in learning more, here are the useful links. So we have the design doc link here, the source code in our GitHub repo, the Python API documentation, and the collabs, and so feel free to check them out. So at last, we invite you to try Beam and these new features, and we appreciate your feedback. There's much room for improvement, so contributions to Beam are always greatly valued. Thank you so much.